Good morning, ladies and gentlemen. Welcome to this video on scientific notation and significant figures. Scientific notation, easy. Significant figures, I think, is diabolically difficult. So, hope you're sitting down, ready to take notes. Scientific notation is essentially used for us to display very large, very small numbers. Significant figures, also abbreviated as Sig Figs by those cool people, are used to indicate the precision of a result. Now note, maths, hence the cartoon, is quite pure, and we don't often need to say how precise our result is because we know exactly what it is. But in every other field, physics, science, etc., down to sociology, when they use numbers, it normally comes from measurement, and measurement has a level of inaccuracy. So therefore they need to show the level of accuracy they're implying by using what's called Sig Figs. And I'll get to that in a sec. Alright, first, scientific notation, and I'm hoping you've seen this before, so I'm going to go quickly. When a number is used in scientific notation, it is written in the form of a times 10 to the m, where a is between 1 and 10. So that number there at the start is between 1 and 10, or -1 and -10, and m is an integer. Excuse me. So m is a whole number. Converting this to scientific notation, we can see that the number here, that is Ra, effectively, it is not between 1 and 10. So because it's not between 1 and 10, we need to take steps to make it between 1 and 10. To make it between 1 and 10, what we have to do is move this decimal 2 places that way. And if we move it 2 places that way, the number looks like this, 1.2354. And we've moved it 2 spots, so that then lets us multiply by 10 to the 2. Sorry, that's a really weird pen. So 10 to the 2 implies a 2 jump in that direction there. Here, we're needing to jump 1, 2, 3, 4 to make sure the number in front is between 1 and 10. So if we've jumped 4 back, note that negative stays in the front. We've become 4.56. And we've jumped 4, making the number bigger, so times 10 to the -4. You can think of as if you have a big number, you'll end up having a big number power up here, little number power up here. Note that if you have a fancy calculator, your calculator might well express this as minus 4.56 e -4. If your calculator says e -4 with a capital E, that e is really the same as times 10 to the power of. It's your calculator abbreviating that times 10 to the power of to make it fit nicely on the screen, I guess. Alright, one more. Here, the decimal number needs 1 jump, so it is, 1.003 times 10 to the -1. If, for some reason, you had a number that was already in scientific notation, like 2.7, you can make it very obviously in scientific notation by writing 2.7 times 10 to the 0. Because you haven't had to jump it anywhere, 10 to the 0 is in fact multiplying by 1. Alright, convert to scientific notation. Let's go in the other way this time. 4 is a big number, it's positive 4, so we're jumping 4 this way. 1, 2, it looks like we've run out of jumps, but every time we have to jump an extra time, we chuck in a 0. 3, 4. So 2 extra jumps is 329, 0, 0. That number and this number are the same thing. Here, we're jumping back 5, 1, and then 4 zeros. So 4 zeros, the decimal place jumped there. It also jumped the 1 and the 5 and the 6. We put a 0 there and the negative here. Make sure you do put a 0 at the front. It's not being jumped, but putting it there makes it very obvious that there is a decimal there. Otherwise, it's kind of easy to miss out the decimal. This here, times 10 to the 1, means we're just jumping 1 this way, making it a bigger number, so it becomes 10.09. Alright, hopefully you've seen that before, and it's not too confusing. We will do some practice on that in the class. Alright, here comes the confusing thing. Significant figures. So, in science, engineering, etc., most of the numbers used are based upon measurements. And because measurements are uncertain, we can only use those numbers that are meaningful. If I take my ruler out and measure the width of my page to be 22.4072643 centimeters, you're going to say you're joking, right? There's no way you could measure that far down using a normal ruler. That's just insane. So the number of digits in a number actually implies a level of accuracy. And if we were writing this, what would make sense is for me to actually say 22.4, and even then, with a common ruler, I wouldn't be probably 100% certain about the 0.4. But 22.4 would be a reasonable shot with a normal ruler. Similarly, in normal conversation, things can have a level of accuracy. If I'm writing it's 8 kilometers from Wk2 to Snell's Beach, or if I just say that in conversation, you'd probably forgive me if the actual answer was 8.4, 7.6, or anywhere in between those two, because I've just thrown out 8.8 kilometers to Snell's Beach. No worries. If I said it's 8.0 kilometers, then that implies an entire new level of accuracy. They're exactly the same number, but they mean different things. This here really means, well, it could be somewhere between 7.5 and he's rounded up because he couldn't be bothered to say two numbers, or 8.4 and he's rounded down, or 8.499 and he's rounded down. However, this one here implies a whole new level of accuracy. If I said 8.0 and the real answer was 7.5, well, that's just wrong. Because I've said the 0.0, I'm insisting that I'm accurate to the nearest 100 meters, rather than without the 0 here, I'm just accurate to the nearest kilometer. If I said this, then I'd be accurate to the nearest half meter, or the nearest meter. So if I said it's 8,012, can't read, what I'm saying is it could be 8,011.9 or 0.7 meters, but I'm implying a level of accuracy down to that last significant digit there. Let me tell you another. Let's call it a fable. It's like a legend, but with a purpose. I guess legends have purpose too. Alright, so why they're significant, or why they're important outside of maths. Don't know why they're interesting maths people teach it, but yeah, outside of maths. So a chemistry student once needed a cube of metal to have a mass of 80 grams. He knew the density of the metal, which told him the cube's volume. Believing significant figures were invented just to make life difficult for chemistry students and had no practical use in the real world, he calculated the volume of the cube to be this. He thus determined the edge, so he took the cube root from the volume, to be this. He took his plans to the machine shop, where his friends had the same type of work done the previous year. The foreman said, "Yes, we can make this according to your specifications, but it will be expensive." "That's okay," replied the student. "It's important." He knew his friend had paid $35, and he'd been given $50 out of the school's research budget to get the job done. So he's thinking, sweet, I'm fine. He returned the next day, expecting the job to be done. "Sorry," the foreman said, "we're still working on it. Try next week." Finally the day came. Our friend got his cube. It looked very, very smooth and shiny and beautiful in its velvet case. Seeing it, our hero had a premonition of disaster and became a little bit nervous. He summoned up enough courage to ask for the bill. $500. And cheap at that price. We had a terrific job getting it right. Had to make 3 before we got one right. But, said the student, "my friend only paid $35 for the same thing." "No, he wanted a cube 2.1 centimeters on the edge, and your specifications called for 2.097. We had yours roughed out to 2.1 that very afternoon, but the precision grinding and lapping to get it down to 2.097 took so long and cost the big money. The first one we made was 2.089 on one edge when we got finished, so we had to scrap it. The second was closer, but still not what you specified. That's why the 3 tries." So we can see, in this story here, that by asking for this measurement, the student was implying he wanted that level of accuracy. However, 2.1, if he just rounded it to 1 decimal place, that would have worked just fine for him probably, and been far cheaper and easier to massage out, or to lathe out, or whatever they did to it. Okay, so there are rules determining the number of significant figures, and you may get a question asking answer to a certain number of significant figures. In reality, you have to think about it logically in terms of what level of application you're at, what level of, sorry, I just got an email that distracted me. In reality, you have to think about what level of accuracy you're implying by each decimal that you're adding on, or each significant figure that you're showing. So I'll go through the dry rules, but the way this works in an assessment for you is very much like this up here.